So whenever you see this definite integral, anytime you see a definite integral with the little lower bound and the upper bound, we're going to say that this is going to be evaluated at f evaluated at the upper bound minus, again, this is a capital F because it's the antiderivative evaluated at the lower bound. And we're calling that inside function lowercase f, so remember capital F is just the antiderivative of our lowercase f. And for us, that upper bound is 3, and the lower bound is 0. So if we have f is x squared, that means the antiderivative is what?
The antiderivative is 1/3, 1 over.
Mm-hmm.
Yeah, sorry.
1/3 x cubed. Yeah, we add 1 to the exponent, and then we divide by our new exponent. Okay, so whenever I plug in 3 for x, this is going to be 1/3 times 3 cubed, minus when I plug in 0 for x, that's 1/3 times 0 cubed.
Oh, plus c.
Okay, so you're right, but we mentioned this last time. Anytime we're dealing with a definite integral, we don't actually have to remember the plus c. If you're just asked about an antiderivative, you should definitely remember the plus c. But the weird thing happens with the definite integral is that if I put a plus c here, and I evaluate this, I would have a plus c, and then I would evaluate the antiderivative at 0, and I would have a plus c. And then we'd have plus c, and you would have minus c, and then they would cancel out. And that always happens for a definite integral. So we don't actually need the plus c's. Those are eventually going to cancel each other out. And then 1/3 of 3 cubed would just be 3 squared, and then anything times 0 is 0. So 3 squared is 9.
Okay. I thought I was just doing nonsense, but I'm actually.
Did you get it?
Yeah.
Awesome.
I
Very
thought I was
good.
actually doing nonsense. I was like, I think this is wrong.
Very good.
I literally just plugged like 3 and 0 into the x squared and just evaluated like that. X3 squared is 9, and then 0 squared is 0, so 9 minus 0 is 9.
Oh.
I kind of.
Like,
So you got
can you
lucky.
say that again?
Yeah.
But that won't work.
Yeah, that won't work.
That won't work in
Yeah.
general.
Also, you just plugged in the numbers.
Yeah.
Oh.
For that specific question, yes, I got very lucky.
Okay, so this question says, find the total area bound between this curve, given by that function, the x-axis, and the vertical line at x equals 0, which would be the y-axis, and x is equal to 3. So I have this curve, and then I have this vertical line at x equals 3. And so let's say that this is x equals 3. And so there's going to be some vertical line here. And whenever x is equal to 0, this whole function would be something times 0 minus 1. So when x is equal to 0, my function value is minus 1. If x is equal to 1, that'd be 1/4 minus 1. That would still be like down here somewhere, minus 3/4. If x is equal to 2, that would be 1 minus 1, so that would be 0. And then if x is equal to 3, that would be 9/4 minus 1, which would be like 5/4. So this curve is going to look something like this. And you can kind of figure it out by taking a few points x and then plotting it, or whatever your favorite method of graphing is. But anyways, this function gives you this curve in the xy plane. And I want to find the total area that's bound up here between this curve, the x-axis, the vertical line here, and the vertical line at the y-axis. So basically the area I'm looking for, I'll draw it in green, is that area plus this area. And that point would be when x is equal to 1, and this point is x equal 2. So we talked about how if you have an area below the axis and you calculate just the definite integral, then that area below the axis is going to count negatively towards our definite integral. And so if you did this, if you said, well, I'm just going to take the definite integral between 0 and 3 of my function, 1/4 x squared minus 1, that's going to give you something that is not correct. And again, it's not correct because I want the total area, so I actually want to find each of these areas and then add them together. So instead, what I should do, I'm going to make this red just so I visually see that this is not correct. Okay. Now, what I should do instead is I should say, I'm going to take just the definite integral between 0 and 2, which will give me that area here below the axis. And since I know this is going to be a negative number and I want it to be positive, I can make that a negative of 1/4 x squared minus 1. And then I want to add to that this extra area, so then I'll add a definite integral that has lower bound 2 and upper bound 3. So that would add the little piece of area above the axis.
So how did you plug in those points? Did you plug in the x0 and x3 within the equation?
You're asking how did I plot this blue curve?
Yeah.
Yeah. So I plotted this blue curve by saying, well, what would happen if x is 0? That'd be 1/4 of 0 squared minus 1.
Oh.
So my y value would be minus 1. I said, what would happen if x is 1? That'd be 1/4 of 1 squared minus 1. So it'd be 1/4 minus 1, which is negative 3/4. And then I plotted this down here at negative 3/4. And then I said, what would happen if x was 2? That'd be 1/4 of 2 squared minus 1. And 1/4 of 2 squared is 1, so it'd be 1 minus 1 is 0. And then when you plug in 3, your function should give you 5/4. So yeah, you're right. I plotted or I drew the picture first. That's always helpful for these types of questions. So I want to add this little piece up here, the second green area. And so I take the definite integral from 2 to 3 now of 1/4 x squared minus 1 dx. Now again, inside the integrand, I'm calling this function lowercase f. In fact, that's what my little problem tells me to use. But basically, if I want to evaluate the first definite integral here, of course I put the negative sign in, and then I want to calculate the antiderivative evaluated at the upper bound minus the antiderivative evaluated at the lower bound, like that. So inside the parentheses, that's the first definite integral. And then for the second definite integral, I'm going to take the antiderivative evaluated at the upper bound minus the antiderivative evaluated at the lower bound.
Is it the halfway point? That's why you put, it's like the, is it because it's above
Yeah.
the line? Oh, okay.
Yeah.
That's why it's upper bound. Oh, like, what are you talking about?
Yeah, you're absolutely right. So I split this into two definite integrals because I know that this area would show up negative. Whenever I just evaluate the definite integral from 0 to 2, that's going to give me a negative result because that area is below the axis. On this other piece of area, that's going to show up positive when I take the definite integral. And so when my question is asking me for the total area that's bound between the curve and the x-axis, then I need to actually make sure that both of those are counting in a positive way towards the area sum.
Yeah, because you were showing us the other day, like that image, like where it's zeroed out because it was even to G.
Mm-hmm. Okay, so if I distribute the negative sign here, then I'm going to have capital F of 3 minus capital F of 2 times, times 2, because I have 2 minus capital F's of 2, and then plus capital F of 0. So I need to evaluate those three things. And first, I need to find what is capital F anyways. So got to make a little bit more room. This capital F is the antiderivative of this. So what would be my antiderivative of lowercase f?
1
Instead of x squared, it's going to be x to the power 3? Yep.
And then you multiply.
And then we divide by the new exponent when we do an antiderivative power rule. And then what's the antiderivative of minus 1?
Just
1x or x.
Thank you, Miguel. Yeah. A lot of people in this class getting your derivatives and your antiderivatives mixed up. Remember, derivative power rule, your exponent goes down by 1, and then you multiply times your old exponent. In the antiderivative, your exponent goes up by 1, and then you divide by your new exponent. So they're like perfectly opposite each other. Okay, so that is the formula for my antiderivative. Now I need to evaluate this at 3, at 2, and at 0. So I'm plugging in x equals 3, and I get 1 over 12, and 3 cubed is going to be 27 minus 3. And so you could call this 27 over 12 minus 3, and you could think of 3 as being 36 over 12. So 27 minus 36 would be negative 9 over 12, which you could simplify to negative 3/4. Okay. Then whenever I plug in x is equal to 2, this would be 1/12 times 2 cubed, where 2 cubed is 8. And then I subtract x, so I subtract 2. So this is 8/12 minus 2 would be like 24/12. And 8 minus 24 is going to be negative 16 over 12. So I factor out the 4, and I get negative 4/3, right? Let me know if I've made a mistake anywhere. And then if I plug in x equals 0, this is 1/12 times 0 cubed minus 0. So that is certainly 0. So down here, capital F of 3 was negative 3/4 minus 2 times capital F of 2. Well, capital F of 2 is negative 4/3 plus 0. That 2 times 4 over 3 would be 8/3. So this is going to be 8/3 minus 3/4. Final answer. And we can double check our work because we can pull up Desmos, and I'll put in my function. It was 1/4 x squared minus 1. And I had lower bound 0 and upper bound 3. And so sure enough, there's some area below the curve, and then it switches to an area above the curve when x is equal to 2, just like we predicted. The green area is 0.58, and the red area is 1.3 repeating. So if you were to just take the definite integral with lower bound 0 and upper bound 3, it would have given you 0.58 minus 1.3. So that would have been wrong if we had just straight up done the integral by itself. But since we wanted this total area, we had to do two separate definite integrals and then add the absolute values. So let's just make sure I had 8/3 minus 3/4.
Yes.
And that should be the same as the total shaded area, the 1.91. Questions about that one? A little bit trickier. Okay. So I'm going to go back to yesterday's notes about section 13.5 just so we can work a few more of these examples. I gave you a lot of examples in the back of yesterday's notes, and we didn't do very many of them. So
So do you want us
let's go do example 8.
to we get the other one?
Oh yeah, if you have it on you, you can do that. You can pull it out. If you don't, that's fine. You can write in like a notebook or blank paper.
How many test questions will this test have?
I don't know. How many questions do you want? Zoe's not here, so there's no one who's like 2 questions or 1 question.
10.
10 questions.
Wait, how many
Yeah.
chapters did we go over? Or like, wasn't it like 3?
We just went over chapter 13. Your test is going to be over chapter 13. So there were sections 13.1, and in 13.1 we just learned about the basic antiderivative rules. So you learned about the antiderivative power rule. You also learned that like e to the power kx, when you take the antiderivative, that is 1 over k times e to the kx plus c. Don't forget that rule. And then also don't forget that the antiderivative of, not that one. The antiderivative of 1 over x is natural log. And the power rule, I forget how to write it. If you have x to the power n,
It is.
then that gives you 1 over n plus 1 times x to the power n plus 1. So you raise your exponent by 1, and then you divide by your new exponent. That's supposed to be n plus 1. Plus c. There you go. So that's what you learned in 13.1. Then in 13.2, we went over u substitutions. So remember the u substitutions that everybody thought was so much fun. But the u subs were like if you had this antiderivative like this,
Oh, it was like.
then we said u is equal to x squared, so the derivative of u would be 2x. And if I solve for dx, that means I multiply both sides by dx, and this would be 1 over 2x du. And then making all those substitutions would give me antiderivative of x e to the power u times 1 over 2x du, and then the x's cancel, and you end up with 1/2 antiderivative of e to the u du, which is 1/2 e to the u plus c, and then you reverse your u substitution, and we say this is 1/2 x squared plus c. was antiderivatives, where you had to choose a u. Figure out the substitution. Take an antiderivative that's strictly in terms of u, because all of your x's should cancel each other out. And then reverse the substitution by plugging back in the definition of u after you've taken the antiderivative. So we did in 13.2. In 13.3, we did integration by parts. And so an integration by parts problem would be something like this. And we had to make a little table. So we said plus, minus, plus, minus. We put x squared here, and then we took the derivatives until we got to 0. And then we put the e to the x here, and we just took the antiderivatives. And then we sort of linked these up like so, where we multiply all of the things grouped together, and we add all of the terms. And so it would have been x squared e to the x minus 2x e to the x plus 2 e to the x plus c as your antiderivative.
Do you want us
as
to
integration by parts.
simplify, like if there's like a 1/2 in front and like a 3, do you want us to like multiply those to each?
Yeah,
Yeah.
and then you can
Like
always simplify your answer. Yeah.
instead of putting like a multiplication sign.
Yeah.
'Cause
Yeah, that's totally fine. I'll accept your answer as long as it's correct. Okay, so we had integration by parts, we had u substitutions, we had our basic antiderivative rules. In 13.4, we talked about Riemann sums and how to approximate an area under a curve by adding up the areas of several rectangles that were evenly spaced with the same width. And then we talked about the fundamental theorem of calculus last time, which was basically making this really creepy, eerie connection between definite integrals and antiderivatives, which, if you properly understand that and appreciate it, it should like give you like goosebumps. Like it should make you feel like, oh, that's too freaking weird, man. Then after the fundamental theorem, today we're doing what we call areas between curves and some application or some word problems. So today is really just practice day, mostly. Okay, but that's all. That's the only stuff that's going to be on your test is 13.1 through 13.6.
So like 2 questions for each section.
Yeah, something like that. I like the idea of doing like 10 questions because you could miss 1 question and still get an A, and you could miss 2 questions and still get a B, and so on. So probably 10 questions.
You should have at least like 4 of them just finding the antiderivative. At least just that.
What do you think? There's probably going to be 2 really basic antiderivatives, maybe 3. There's going to be probably 2 types of u sub, like maybe one with, I don't know, we'll see about the u subs. Probably 2 u subs, probably 2 integration by parts. One of them is going to have an exponent and a polynomial, and one's going to have a logarithm and a polynomial. Remember how to do those? Yeah, so remember with the logarithms, if you have like x natural log x, then you put the natural log in the second column and you put the x in the third column. And so we do plus minus plus minus.
So it's the derivative?
The derivative of
And
natural
the
log
antiderivative.
is, yeah, 1 over x. And then the antiderivative would be 1/2 x squared. And the weird thing about these, as we said, we're going to link them up like that at first, and then we were going to do like a little completely horizontal group. And the thing about doing a completely horizontal group in integration by parts is that you still have to take the antiderivative.
Oh.
So for this type of question, you'd have 1/2 x squared natural log x. And then for my horizontal group, we would write minus antiderivative of 1/2 x squared divided by x, but x squared divided by x is just x. And so this whole thing together is 1/2 x squared natural log x minus 1/2. And then the x becomes 1/2 x squared plus c. And then don't forget 1/2 times 1/2. Like Diana was saying earlier, we can just combine that into a quarter. So there's going to be 2 integration by parts. One of them will have an exponent, and one of them will have a natural log. Probably 2 u sub, maybe 2 or 3 antiderivatives with just the basic rules. So that puts me at 7 questions. And then you're going to have 3 more. Probably one of them will be like a word problem, one of them will just be a plain old definite integral, and one will be like an area question where you have to reason about the areas and probably split it up into multiple. Kind of like the one on your quiz.
Yeah.
Yeah. Like the second question on your quiz, there might be a question like that. Okay, so let's do number 8 finally. Let's do example 8 on your notes from last time. So seeing this, I'm going to call the integrand lowercase f, and I'm going to interpret this definite integral as being capital F of my upper bound minus capital F of my lower bound. That is what the fundamental theorem of calculus taught me last time. Then my capital F function is just the antiderivative of my lowercase f. So figure that out.
Okay.
Do the antiderivative of lowercase f in the whole. We'll talk about it in 30 seconds. I don't know if we're going to need these today, but I'll pass them out.
Alright. I think we're good. I think 2 6 1
Okay, it's been 30 seconds. So my antiderivative here, I add 1 to the exponent, and then I divide by my new exponent so that 3 goes away, and I just get negative x cubed. Then I add 1 to the exponent, and then I do 6 divided by 2, which is 3. And then instead of a 4, I have a 4x. And remember, I could add the plus c here because this is an antiderivative, but then again, I know that this is a definite integral, so even if I do add the plus c, it will end up canceling itself out. So whenever I plug in 3 for x, I get negative 3 cube, and what is 3 cube?
27.
Thank you. Negative 27. Plus 3 times 3 squared, which is
27.
27. Awesome. Plus 4 times 3, which is 12, so this is just 12. then if I plug in x equals 0, this would be negative 0 cubed plus 3 times 0 squared plus 4 times 0. So that is 0. So then I have 12 minus 0. So this definite integral evaluates as 12. And, you know, on your test, you're not going to be able to use Desmos, but it's nice to still have like a really strong imagination and be able to like sort of carry these pictures in your head. It's, what am I looking for? Snipping. I do this because otherwise I can't remember what to type into Desmos. Okay, so our function was negative 3x squared plus 6x plus 4. So this is what that integrand looks like, that blue curve. And for us, our lower bound was 0 and our upper bound was 3. And so it turns out that if we were actually looking for, you know, the integral between 0 and 2.528, we would have had a larger value of my definite integral. But going all the way up to 3 included some of this red area. And so the value of my integral ended up being 12 because I had to subtract off a little bit. So that's the picture of what this looks like, evaluating that integral. Let's try example 12. That one looks suspicious. It looks a little bit sketchy. So let's make sure we can do this together. It's funny because you know, you really haven't seen the entire scope of calculus, because in business calculus we're just trying to show students like the highlights. You know, what are the most important, what are the simplest cases, you know, where you might use this in your life. But just in general, like talking about all of calculus, if you were to take the calculus courses 1, 2, and 3 over 3 semesters instead of just 1 semester of calculus, you'd find derivatives, no matter what the function is, even if it's like trigonometric functions and stuff, derivatives are always easy to find, and it's always like possible. Like maybe it takes you a while, maybe it takes you, 30 minutes or more for like a really difficult derivative, but you can always find it, for sure. Antiderivatives are always a little bit intimidating even to like mathematicians, because there are some antiderivatives that you cannot find, period. There's no methods available for you to be able to find the antiderivative. So there's like things you do to work around this, which again, you would learn some of those workarounds if you took like calculus 2, for example. But like this antiderivative can't be found with pencil and paper. This doesn't work, doesn't happen. And so whenever you're like approaching one of these antiderivatives, if you find an antiderivative question in a textbook, you can be pretty certain that the textbook isn't going to throw you one of these weird ones. But if you just come up with your own examples, or if you just see an antiderivative out in the wild, you have this like feeling in the back of your head like, oh, what if I like work on it for a really long time and it turns out it's one of those that you can't find, period, you know? So basically, what you would do if you had the antiderivative e to the power x squared, you say, well, shoot, this is, Desmos can do it, right? Like Desmos can still evaluate like a definite integral of this thing. But notice it's not actually telling me the antiderivative. What Desmos is doing is it's taking that Riemann sum. It's adding a bunch of like, rectangle areas. And so every sort of method for evaluating that antiderivative essentially boils down to the same idea, is that you're just coming up with an approximation that's just as close as you would ever want it to be. So you can still evaluate integrals with that integrand, but you can't write down an antiderivative for it. Anyways, so whenever I see something that looks a little bit sketchy, part of me thinks like, oh let me just try really hard and I might be able to solve it. And then part of me thinks like, oh, I hope it's not one of those that is gonna like. I hope that there's possible to find a solution to this. Anyways, let's try u sub. What should my u be?
The square root of the natural log of y.
Yeah.
I'll do you one better. We're going to do just the natural log of y.
Oh.
Okay, so then du dy is going to be what?
1 over x.
Yeah, it'll be 1 over y in this case. It's my variable. So I need to solve for dy, so I can substitute that. And that tells me that dy is going to be y times du. And so this is going to be, well, so it's a definite integral, right? And so I need to first find the antiderivative of this integrand, and then evaluate it at 4, and then also minus capital F evaluated at 1. That's my eventual goal. But I'm going to rewrite that integrand as the square root of u, instead of the square root of natural log y, divided by y, and then instead of dy, I'm going to write y du. So then the y's cancel, and this is just square root of u. And if I take the antiderivative, then the antiderivative of square root u is going to be...
What did you say? Square root of u?
Yeah, so if my function lowercase f is square root u, what's the antiderivative of square root u?
3 halves u.
Okay, so Miguel's on to something. Square root u is u to the 1/2 power. But now what's my antiderivative power rule?
Divided. Or you divided the...
Your exponent is up 1 and then you divide by the exponent.
Yeah, so you
Okay.
add 1 and then you divide it. In
Yeah.
the front.
To my exponent, I add 1. So 1/2 plus 1 is 3 halves.
And then you put your root.
Then I need to divide by 3 halves. So I could write 1 over 3 halves. But 1 over 3 halves, remember, is the same thing as 2/3.
Oh, yeah.
Yeah. If you were going to divide by 3 halves, well, dividing is the same thing as multiplying by the reciprocal. The reciprocal of 3 halves is 2/3. So instead of dividing by 3 halves, I can multiply times 2/3. Okay. So then also remember that u, the definition of u was natural log of y. And so I'm talking about 2/3 times natural log of y raised to the power 3 halves. Okay. So I need to find what is capital F when I plug in x is equal to 4. Or sorry, I should say y is equal to 4. I let y equal 4. This is 2/3 times natural log of 4 all to the 3 halves power. And you would have to plug this into your calculator. Right, on an exam you'll have that little TI-30 in front of you. So you would first plug in what is natural log of 4, and then take that number and raise it to the power 1.5, or 3 halves. And then you'd multiply whatever you get by 2/3, and that would give you some number.
Some.
Yeah.
And then you plug in 0.
And then...
I mean 1.
Yeah, and then we plug in y is equal to 1, so that would be 2/3 of natural log of 1, all raised to the 3/2 power. But natural log of 1 is
1 over... No.
0. Yeah, so this is 2/3 times 0 to the 3/2 power, so it's all 0. In any case, it turns out any logarithm function is always 0 whenever you evaluate it at x equals 1. So like if I have natural log of x, whenever x is equal to 1, the function goes through 0. If I have logarithm base 2 of x,
1.
that's also 0 whenever x is equal to 1. If I have logarithm base 10 of x, it goes through 0. And if you have logarithm with, I'll just put c, and you just let c be any base, a logarithm always passes through 0 whenever x is equal to 1. So, sort of the reason for that is you have to remember, and honestly I have to remember this too, I always forget, but I need more space. So the way that we define the logarithm, basically the definition of like what the logarithm function is that the natural log, whenever I plug in e to the power x, so the exponent with base e, this is just equal to whatever x is, right? And likewise, if I take e to the power natural log of x, that is just x. So we're basically saying the natural logarithm is the function that is the inverse function of the exponential function. So if I have the natural log of 2, for example, we're saying that e raised to what power gives me 2? And it turns out e raised to the power 0.69 gives you 2. So we say natural log of 2 is 0.69 exactly because e to the power 0.69 equals 2. That's the whole reason, right? And likewise, if I were to say, somebody tell me the logarithm base 10 of 1,000, we're asking the question, 10 raised to what power gives me 1,000? And this is 3, exactly because 10 raised to the power 3 is equal to 1,000. So anyways, why is log base anything of 1 equal to 0? Because we're asking e raised to what power gives me 1? Well, e raised to the 0 power gives me 1. Also, if I had log base 2 of 1, I'm asking, well, 2 raised to what power gives me 1? Well, 2 raised to the 0 power gives me 1. Yeah, anything to the 0 power is 1, so logarithm of 1 is always 0. I know logarithms are so difficult for me to remember. Like, I totally understand if you've forgotten since your algebra class.
We kind of learned that part in the last nice. Yeah.
That's good.
She was making us do both ways. So like she would test us on like iron and then blah blah, and then we'd have to make the like we would flip it or like do it in the other way. She would make us do it.
Yeah. Yeah, another thing is maybe in algebra, they should have taught you that a function and its inverse, like natural log and the exponent base e, they have a sort of geometric pattern to them, where if you reflect one of the curves across the line y is equal to x, then you get the other curve back, right? And so the one on the bottom, this is the natural log. The one on the top, that's the exponential function. And so whenever you have e raised to the 0 power, that gives you 1. And then if you reflect that point 0, 1 across this blue line, y is equal to 0, that point reflects to the point 1, 0, which tells you that the natural log evaluated at 1 gives you 0. So, anyways. Did anybody plug this into their calculator? Did you figure out what is natural log of 4?
Just the natural log of 4?
Uh-huh.
1.38?
Yes. Yeah. Should be 1.38. And what is 1.38 to the power 1.5?
1.63?
Okay, so then what's 2/3 times 1.63?
Oh, I already did the whole thing. It's 1.088.
Cool.
1.
So then capital F of 4 is 1.089. I'm sorry, 1.09, I guess, for 3/5 sig figs. And then capital F of 1 is 0, and so this whole definite integral should evaluate to 1.09. Let's see if Desmos agrees with us. We've got square root natural log y over y. And I don't know why it doesn't like that. Try that again. Square root natural log y divided by y. What is wrong? Oh, ha! I need x instead of y. Third. Ooh. So that's what my curve looks like. I need to take the definite integral between 1 and 4, which would be that area. And so sure enough, Deanna plugged it in her calculator correctly because the value should be 1.0881, just like she said. Okay.
Oh, we won't have this.
So then let's talk about the notes for today. And the notes for today are really kind of short. The only new thing that we're learning is that you can find the area between two curves like this. You kind of determine, and you might have to graph both curves to figure out which curve is going to be on top and which curve is on the bottom. Then you're going to figure out where do these two curves intersect each other. And you can do that just by setting your top curve minus your bottom curve equals 0. So when the difference between your curve values is 0, that means they're intersecting. And then you solve for x. And then finally, step 3 means you're going to set up a definite integral with your integrand being your top minus your bottom. That's going to be our f function. And we're going to use those intersection points as our lower bound and upper bound. So wherever the curves intersect, that's going to be the lower bound and the upper bound. So consider this question. It says, example 1, find the area bound between the curves y is equal to x squared and y is equal to 1 minus x squared. So draw a little picture. Pictures help you think. So here's my xy plane. Y equals x squared is just the parabola that looks like that. And 1 minus x squared would be a downward facing parabola when x is equal to 0, y is equal to 1, and then it's going to have the same shape but just in the downward direction, so it'll look like that. And so when my question is asking me find the area that's bound between those two curves, this is the area it's talking about. What's this area between the red and the blue curves, right? So then let's look at my procedure. Number 1, we're going to say that the red curve is my top curve because in that little lime green area, the red curve is on top. And so red curve, you are now top curve. Blue curve, you are the bottom curve. Step 2 says I need to determine where do these two curves intersect. We see there's 2 points where the curves intersect each other, and we can find that by setting up an equation. And in my equation, I'm going to say my top curve minus my bottom curve is equal to 0. So just simplifying, I have positive 1, and then I have minus 2x squared equals 0. And so again, solving for my x values, I'll subtract 1 from both sides and divide both sides by negative 2. So negative 1 divided by negative 2 is positive half. And if I take the square root of both sides, my x values are going to be at 1 plus or minus square root of half. So this x value is positive square root of half. And this x value down here is going to be negative square root of half. So now step 3 says we're going to calculate a definite integral where the integrand is the top minus bottom. So the integrand, in other words, for us is going to be like 1 minus 2x squared. That's the top function minus my bottom function, red minus blue. But I'm going to use the intersection points as the lower bound and the upper bound. Excuse me. So my lower bound will be negative square root of half, and my upper bound is going to be positive square root of half, like that. And we know how to evaluate definite integrals. We're going to tell ourselves that this integrand is named lowercase f, and that means I need to take the antiderivative, capital F, evaluate that at square root half, and then subtract the same thing, capital F, now evaluated at negative square root half. So first step then would be to find what is my capital F function. So we want to find the antiderivative of 1 minus 2x squared. So the antiderivative of 1 is going to give me x. The antiderivative of x squared would give me x cubed. Then I divide by 3. So capital F is going to be x minus 2/3 x cubed. If I plug in square root of 1/2 here, I'm going to get square root of 1/2 minus 2/3 times square root of 1/2 cube. And on your test, I will hand you a TI-30 calculator, so you'll have it next to you. And you can plug in square root of 1/2, and you can figure out what is square root of 1/2. I think it's like 0.71 or something like that. Somebody tell me. Square root of 1/2. Square root of 0.5.
0.7.
Okay, 0.7?
0.7.
So, I was right, it was 0.71. Okay, minus 2/3. What is 0.71 cube? .34. What is it? 3.6. Ah, man, that was my close.
0.3579. So I would do
It's 0.36, yeah. Okay, so 2/3 times 0.36 gives me 0.24. 0.71 minus 0.24 is going to be 0.47. Yes. Cool. So that would be, that's one thing. That's capital F evaluated at positive root half. What would be capital F evaluated at negative root half? Well, root half is 0.71, so negative 0.71 is what we're trying to plug in here. And that means I have negative 0.71, and that is going to be negative even after I cube it.
Wait, can't you not
So
have
it's going to be like,
negatives under the square root, under the square root? Like a negative.
huh?
Can't you not have negatives under the square root?
Yeah, it's not under the square root though. This is outside of the square root. This is just plugging in my lower bound here,
Oh, okay.
which is negative square root of half. Yeah. Okay. And then, again, just to reiterate, my definite integral that I'm trying to figure out is capital F evaluated at positive square root half minus capital F evaluated at negative square root half. So that's 0.47 minus negative 0.47, which is 0.94. So that was a long problem, and I should have left myself more room on my little notes page to do it. Well, let's just see if it works. Let's plug in. Oh, I guess it occurs to me that this isn't completely ready to go to do areas between curves. But I can still start from where we took the definite integral between negative root half of and positive root half of 1 minus 2x squared. 1 minus 2x squared. And my lower bound is going to be negative square root of half. My upper bound is going to be positive square root of half. So that area should be 0.94. And that's what we got. Okay, so are there any questions about the procedure for doing this, or are there any questions about what we did there in example 1?
It's just like longer,
How
or
did
like
we
another
get-
step to that
Yeah.
area
How
bound.
did we get 0.94 in it and it didn't zero out? Because I saw the zero in the decimals.
Yeah. So if you evaluate capital F at negative, at the lower bound, negative square root half would be negative 0.71. We got negative 0.47. And whenever we evaluate a definite integral, we take the antiderivative of the upper bound minus the antiderivative of the lower bound.
Oh,
So it would have
ended up
been,
adding.
yeah, 0.47 minus negative 0.47.
Okay.
Good question. Good question. All right, in the next 6 minutes, we're going to work example 3. So example 3 says, suppose Frito-Lay earns revenue according to the following function, where R prime is the rate of revenue in millions of dollars per year. So remember, a lot of times we interpret the derivative as a rate of change. And so if you're talking about total revenue, well, the rate of change of total revenue would be R prime. And that rate would be in dollars per year, or in our case, in millions of dollars per year. So we have a function for revenue. We also have a function for costs, and it's the same. It's in millions of dollars per year. And so the rate at which we're earning profit is going to be the rate at which we have brought in revenue minus the rate at which we have to pay our expenses, or the pay our costs, right? So profit is money in minus money out. It's revenue minus expenses, or you could say revenue minus cost. Now, the question asks, what is the total profit earned by Frito-Lay during the 5-year period from 2010 to 2015? And since t equals 0 corresponds to 2000, this is going to be the period between t is equal to 10 and t is equal to 15. Well, I would start by finding out what is my p prime function. What's the rate at which I'm earning profit? And so I would do 0.05 t squared minus 0.04 t squared, and that would give me 0.01 t squared, because I'm doing revenue minus costs. And then for my t terms, I've got negative 0.05 t minus negative 0.06 t, and that's going to be plus 0.1 t. So I'm subtracting a negative, means like I'm adding 0.6 to negative 0.5. And then I have 20 minus 15 is plus 5. And so I have my profit, or my rate of profit function. So this is giving me profit in millions of dollars per year. And I want to know what's the total profit made between t10 and t is equal to 15. And so what we have to do to sum up the total profit that's earned according to this rate function is we're going to have to take the definite integral from lower bound 10 to upper bound 15. And to evaluate a definite integral, that means we take the antiderivative of that inside function. So the antiderivative of p prime would just be p. And then I evaluate that at the upper bound, which would be 15. And then I subtract the same antiderivative function evaluated at the lower bound, which would be 10. So I need to find what is the antiderivative of p prime. I'm just going to call it p. Well, t squared is now going to become t cubed, and then I divide by 3, so it's 0.01 over 3. And then t is going to become t squared, and I divide by 2, so that's going to be 0.05. And then that 5 is going to become a 5t. So then you plug in 15, and we find that p of 15 would be 15 cubed, which is a large number. What's 15 cubed?
15 cubed
Uh-huh.
is 3375.
Okay, then divide by 3. 3375 divided by 3.
1125.
And then multiply times 0.01.
11.25.
Okay. So then my first term would be 11.25 because we just did 0.01 divided by 3 times 15 cubed. And then 15 squared is 225. 225 would divided by 20 would be like 11.25, I think. And then 5 times 15 is 75. And so this is 75 plus 22.5, 97.5. That would be p of 15. Then I have to subtract p of 10. So p of 10 would be 10 cubed, which is 1,000, times 0.01, which is 10, so 10 thirds, plus 100 divided by 20 would be 5, plus 50. So 55 plus 10 thirds, 55, 58 and a third. Oh, minus 58 and a third. So 97.5 minus 58.5 is going to be 39.2. Is that right? Or is that wrong? Could be wrong.